enough positively charged ions enter the cell through the gap junctions, and the inactivation gate is open, and then the activation gate opens, sodium floods into the cell. Okay, why? Because it's following an electrical chemical gradient. There's a chemical gradient where sodium is at higher concentration outside the cell compared to inside. That influences its influx. But also there's a voltage gradient, an electrical gradient, where the inside of the cell has a negative charge, the outside has positive, so sodium also follows its electrical gradient. So threshold is reached, sodium is going to flood into the cell until the inside of the cell reaches about positive 30 millivolts. Okay, by this point, the inactivation gate has closed and no further depolarization occurs. These voltage-gated sodium channels are considered fast channels because once threshold is reached, these channels open up very quickly. Whereas calcium channels are considered slow channels. They open up more slowly. So as voltage-gated sodium channels open, you have a rapid sodium current that enters into the cell, and the cell depolarizes. Okay. Again, now, I'm not saying negative 90 at rest. That's just an arbitrary number. If you were to measure transmembrane potential around different parts of the heart, some parts it might be negative 80 millivolts. But the idea is the same, is that when positively charged ions enter the gap junctions, the membrane partially depolarizes. If it reaches threshold, then those voltage-gated sodium channels open, and the cell completely depolarizes. Okay? Now, this resting membrane phase is called phase 4. Depolarization due to the influx of sodium here is called phase 0. Phase 1 is this initial repolarization. This initial repolarization is triggered by opening of potassium channels. There are different types of potassium channels, but at peak depolarization, potassium channels open, and if potassium begins to leave the cell, the inside becomes more negative again, and the cell begins to repolarize. So notice that repolarization begins with opening of potassium channels. That's called phase 1. We then reach a plateau phase. Even though these potassium channels are still open, the slow opening of calcium channels that allows calcium, positively charged ions, to move into the cell, and that blunts the repolarization. It creates a plateau phase, which is called phase 2. These potassium channels that open are called L-type slow calcium channels. Now, at the end of the plateau phase, calcium influx ends. Those channels close, and a new set of potassium channels open. As more potassium leaves the cell, it repolarizes back to rest. Resting membrane potential. So phase 2 is the plateau phase. Phase 3, which is the terminal repolarization, is brought about by potassium efflux out of the cell through what are called delayed rectifier channels, a different set of voltage-gated potassium channels. So, phase 4, 0, 1, 2, 3. This shows you the position of the voltage-gated sodium channels during each phase. During phase 0, both gates are open. At peak of depolarization, the inactivation gate has closed. Okay? It's only when the cell is almost completely repolarized that that inactivation gate opens again and the voltage-gated channels reset. shows the typical fast, and this is called a fast response action potential. This is the type of action potential that's present in non-autoretic cells, typical myocardial contractile cells. It shows you that at rest in phase 4, potassium conduction is high. And potassium is moving through voltage-gated channels. During depolarization, what happens is potassium conduction decreases, but sodium conduction through open sodium channels increases. And that brings about that depolarization. Okay? Then during phase 1, what's happening is potassium conduction begins to increase as potassium gates open, and potassium effluxes out of the cell. Okay? During the plateau phase, the reason we have the plateau is because the potassium movement is balanced by calcium movement through those L-type calcium channels. So this matches the movement of ions to the action potential. Now, once a cell depolarizes, the proximal membrane depolarizes, that wave of depolarization spreads as positively charged ions are attracted to neighboring segments that have a negative charge, bringing those segments to threshold and opening more voltage-gated channels. This is your action potential in blue. In red is a graph of muscle contraction, of tension. What you can see is that the electrical event, the action potential, is what triggers generation of tension, muscle contraction. Now, when a cell is undergoing depolarization and repolarization, okay, through most of that period, the cell is in what's called an absolute refractory period. That means from this point to this point, from the action potential, the cell cannot receive another stimulus. It will not respond to another stimulus. Okay? That's called the absolute or effective refractory period. So it extends through most of repolarization. The terminal part of repolarization brings us into the relative refractory period. During the relative refractory period, the muscle cell can respond, but it requires a stronger than normal stimulus. That's called the relative refractory period. Okay. So what we talked about today was fast response action potentials, the type of action potentials that occur in regular myocardial cells. These fast response action potentials are generated by opening of voltage-gated sodium channels. So the depolarization is the direct response to the influx of sodium. Re-Polarization, on the other hand, is due to the efflux, outward movement of potassium. As potassium leaves the cell membrane again becomes polarized, more negative, and returns to its resting state. Now, that's all we're going to talk about with regard to electrophysiology today. This is information that's in your book. Okay, did everyone read that chapter 2? I will have to be honest with you. You can't read it like a novel. You can't read it quickly. Every word has meaning. Okay? So, you may not understand it the first time you read through it. But then after going through the notes, read it again. Read it again. Next class, we're going to finish up electrophysiology by talking about slow response action potentials, the type of action potential that we see in pacemaker cells. Okay. And then we'll work on maybe some questions in the back of the chapter. Some questions. How many people, don't get ready for you, feel pretty dang good about themselves now? Good. You understand to the point where you can go back and review, and you can move forward. What I'm concerned about is someone who's completely lost. And it's okay to be completely lost, but you just need to let me know. Yes? The fast response action potential occurs in regular myocardial contraction cells, in the atria, in the ventricle, and in the kidney fibers. Okay?
Yeah.
Whereas when we get to the SA node and the AV node, those are slow response action potentials. I found this in my mailbox. I guess all the teachers that are teaching in class have this little gift.